Well, welcome back, folks. For today's class, we pretty much see what we're going to be doing next, going down to section 5.1 to start us off. But also, I'll be posting pretty soon the solutions to our exam one. There's one person with a valid reason to take the exam later on, so I haven't released that just yet. And if you have questions on your exam one, I'll be happy to help out later on, and we can discuss them as well when we return on Monday's class. But for the other big announcements, Quiz 3 is due today. A lot of people turn these in a little bit ahead of time before the exam. And the quiz number 4 is now posted. Quiz 4 is going to be kind of a redo of doing the box plot kind of problem. This one makes it pretty commonly onto an exam 2 situation. So you might expect to do this again. If it doesn't make it onto exam 2, because we're not trying to make our exams super long, not everything can make it on there. Oftentimes, this does make it onto a final exam somehow, some way. So same kind of information that we're going to do down below. You'll start with the 5-number summary, use a 1.5 IQ or rule of thumb, and then construct a box plot. You can use as a guide the problem that we did in class in the class notes. But also keep in mind, just as a reminder with quizzes, they're really just a class participation kind of credit. So you're welcome to work amongst each others. You're welcome to ask me questions. I'll be happy to help out. Once you turn in your quiz, it's considered finalized. But if you have questions on, maybe you're just wondering if it came out right, or if you said enough in the description, you're always welcome to run it by me. I'll be happy to discuss the problem with you. So this one is about triptan. I'm not sure if I'm pronouncing that right. It's for acute migraine headaches and cluster headaches. And this was the amount of time after they had a headache, they took the medication, and they experienced alleviation of their symptoms. So pretty interesting data, serious data as well. That kind of stuff can be kind of just life ruining practically when it's at its worst. But any other questions or comments, folks, before we start today? Okay, well, another comment that started out before class began is if we have another visitor, possibly Sam again, he might want to visit in our class a couple more times. If you're curious on if he's ever in class, you can always just check up here. And if it's a student, I usually pop out that window if a student joined the Zoom class, just so that I can see what's going on with that student. You might use a thumbs up button or something like that if there's ever a day you had to participate through Zoom. So that's how you can really tell if there's someone from the department watching, see what's going on in the class. But aside from that, here's where we sort of left off last class. We just ended after looking at the notes pretty much. We're looking into a new formula called the z-score formula, which is a nice kind of ruler type metric to determine if observations could be considered pretty unusual. We already have the 1.5 IQ or rule of thumb to tell us if something is considered an outlier or not. And this gives us another way to determine if observations are unusual. So the way it's computed is we take whatever data value the problem is concerned with. I'll usually highlight that in yellow on these notes. We subtract off whatever the mean is. That'll be blue in the notes. And then we divide by the standard deviation. That means the z-score automatically has units. If you're dividing by the standard deviations, this is going to be equal to number of standard deviations. Y is from the mean. I'll just say let's say the mean Y bar. So it's just a literal distance. And we know standard deviations also describes how spread out data is. So we might also want to know what's unusual. Well, for a really rough rule of thumb here, any observation two or more standard deviations away from the mean is unusual. If there are 3 or more standard deviations from the mean, that's highly unusual. 4 and more standard deviations away is becoming exceedingly exceptional, and so on. But that's a good way to think in terms of just a basic rule of thumb, kind of like the 1.5 IQR rule of thumb, except this is less about outliers and just more about how far away is it in terms of how extreme is it. So that's how we calculate it. This is the same formula, but not in words. The z-score tells you how many standard deviations or data values away from the mean. I guess that's kind of what we wrote down here, but at least we're really emphasizing that. And it could be either positive or negative. Your z-score is going to come out positive when the data value is larger than the mean. And that makes sense. It just means the numerator is positive if y is larger than y bar. If you see negative, that means your data value y was below the mean. And find the formula, that's because y is less than y bar. So the sign of the z-score also tells you, are we above or below the typical observation, the center, the sample mean y bar. So we'll practice using this formula in a couple different ways. The major use that we're going to see is this z-score can be used to essentially compare things that are very unlike. Here's a kind of a generic example, but this could be used in any kind of setting. Student who took 2 national tests got different scores on those tests. Those tests have their own means and their own standard deviations, and we can tell which test the student actually did the best on. There's a couple more scenarios just like that on the homework as well. So to start out, I have kind of a silly problem that we can tell we copied this one from last year. I was going to update it, but Windows 10 had me doing this a certain way. I couldn't figure it out for Windows 11. There's got to be a weather app here on somewhere. But anyways, I just copied this over from last year. It makes it interesting in a way. We're on September 25th. I think the highs today was about 80, so kind of in line with what we had last year as well. So this was a weather application on a desktop Windows 10 computer. Gave this information for the month of September on the highs and lows. So September 1st was crazy, high of 91 and low of 47. We're going to focus on just the highs in the data that we see. And for this particular data, when I crunch the numbers, the sample mean came out as 76 degrees Fahrenheit. In September, that's not exactly balmy or heading into autumn. Standard deviation was 11.1 degrees Fahrenheit for these data, just considering the highs. So given all that information, it asks us to start out, calculate the z-score for the temperature high on September 1st. Because it looks unusual, right? We want to know, was it really unusual? We have a benchmark for that. If it's more than 2 standard deviations away, it'd be positive because that's above the mean. We'll call that an unusual observation. So we're concerned about what's going on with the 91 degrees. For strategy here, this is really the second big set of formulas. In 1.5 IQR rule of thumb was the first one. The next big formula that we're going to need for exam 2 is the z-score one. Sure, you know you can just jot this down in your notes, but the more you write this down, the more it just is going to work its way in your head. It's going to be something that you're going to memorize eventually. And the more you memorize about it, the easier it is to use. So really good strategy is every time you use the z-score formula, just write it down. It's y minus y bar, divide by standard deviation, S. And just the action of writing it down helps us connect. Well, we have a y bar right here we're using, 76 degrees. We have an S we're using, 11.1 degrees. We'll substitute that into the problem. We just need to know what y is. It said to calculate the z-score for the temperature high on September 1st. Usually this is the hardest part about the formula. What's the data value? That's the thing that's going to be y, and it's often, but not always, it's often the question of the whole problem. So when they said for the temperature high on September 1st, they're talking about the data value in question, and that was the 91 degrees, just the high. So I think that's the hardest part of getting started with this formula. We have to read through the context, know which part goes right exactly here. But does that make sense to everyone, just getting started with it? Okay, from here, it's just another set of substitutions. Kind of like using the 1.5 IQ rule of thumb, we have several different objects here. This is a formula with 4 variables, so really it's a lot going on. Z is a variable on the left, it's solved for, so we're just going to get a number. 3 variables on the right, so anything you can do to organize is massively helpful. We'll take and import the 91 degrees. I'll drop units at this stage and just write 91. The units do cancel because there's degrees Fahrenheit in the denominator that just cancels it right out. So there is no degree unit on this any longer. The unit is standard deviations now. So we subtract the sample's mean, 76 degrees Fahrenheit. We divide by the sample standard deviation, 11.1. Following the colors, this is what we would get. So now it's just back to the calculator at this stage. I'll do this in a couple ways, just for the sake of variety, since everyone likes to compute slightly different sometimes. Some people would rather follow order of operations and go 91 minus 76, then hit enter right there, and then do the division next. In these calculators, it's actually kind of convenient. Whatever number is up here, hit divide, and ANS, prior answer, is really saying 15 divided by whatever you input. We'll put in 11.1. And this is the value we get as a z-score. We're going to 1 decimal place, so this would round up this time to 1.4. If you leave it as 1.4, that's totally fine, but I would encourage you to say 1.4 standard deviations, because that's going to help us with the interpretation part. You can even say a little bit more. This is 1.4 standard deviations above the mean. That's a good thought to connect, because some questions are going to ask you just this part, how many standard deviations above or below the mean is some data value, and you have to know they're talking about the z-score. Other times they just say calculate the z-score and then interpret what we've got. And this is pretty much the interpretation. We just have to involve the context with it. So going by our blunt but effective rule of thumb up here, observation 2 or more standard deviations away, whether it was a positive 2, maybe a 2.5, or a negative 2, negative 2.1, those are more than 2 standard deviations away. That's starting to become unusual. So actually, in fact, 90 degrees is not unusual. And it really feels like it is, right? When we're talking 76 degrees for the average, but the average is not the full story. The variability, how spread out the temperatures are just as important. The variability is actually pretty high in September. 11 degrees is a lot. That's why this is not too unusual. It's just on the high end of that variability. So we can say here, when we go to interpret the context, the high of 91 degrees Fahrenheit on September 1st has, or let's say is, maybe was is the better word there. Choose your verb, I'll go with was 1.4 standard deviations above the mean. Feels like we really just repeated what we said, but we brought in the context of the number when we talked about the high of the 91 degrees. If you mentioned the rule of thumb, I'd say that's a great answer, but it wouldn't be specifically required for this problem. It's just more thinking about what's odd when it comes to a z-score. So let's add it here just as extra information. This was not too unusual. because being within a couple standard deviation is kind of typical, we'll have a rule, another empirical rule that discusses this a little bit better. Being beyond 2 standard deviations, that's when it becomes less typical altogether. But we did it, folks. That's our first z-score computation. Any questions at all about using the formula or interpreting the result? Okay. Well, this question can be asked in a lot of different ways. So we're going to see another example after this one. And often there's multiple parts as well. Here's another way the question can be asked, which is slightly annoying, because this one says, suppose that the temperature high on September 13 turns out to have a z-score of negative 1.73. And it's a suppose because we're making up information. We're just saying, what if? What if it had that z-score negative 1.73? We know what the temperature was. It's 69 degrees on September 13th. But that's not the answer to the question. We're saying, if it had a z-score of negative 1.73, what was that actual temperature? It's still using the z-score formula, but now z is the known quantity, y is the unknown quantity. So it feels like a different problem in a certain sense. It's backwards in a certain sense. So we'll try this out again. We're going to need to cite the mean and the standard deviation. We'll just carry it down and reference it. I guess that works there. We're also going to need the z-score formula, so it's convenient it's there as well. But before we launch into this problem, everyone comes into this class with a different background in algebra. Some people are pretty great at it. Some people are a little bit rusty. And this is the first really full-on algebra problem that we would have to do. There's actually not a ton of them in the class. Most of the algebra looks more like this: substitutions, computations. Occasionally we have to solve an equation, and this is one of those rare kind of times. So I felt like before we just solve this problem, let's do a warm-up to it just to see what the strategies look like. So here's our warm-up. The kind of equations that we're going to be solving in chapter 5 are very, very limited, and this is about what it's going to look like. Something like, I'm just going to make up random numbers. 14 equals the unknown we typically think of as x, but we'll put it in as y because that'll be suggestive with what we're about to solve. So imagine you're solving for y. And the formula goes 14 equals y plus 173 divided by 94. So if we had to solve that, and depending on how rusty you are in algebra, it might not be the funnest thing. If you're pretty fluent, you've done a lot of these before, it probably feels like a breeze. Some people might just put it all into the calculator, and that would be a fine strategy as well. I'm not going to emphasize the steps on algebra, but figuring out, practicing it, it's good to show those steps. So here's what I would do. Eliminate the denominator. It's the hardest thing about the equation. So I'm going to immediately multiply both sides of this equation by the 94. In the calculator, this is what it looks like. 14 times 94. And you'd have that number. On paper, it looks like this. 14 times 94 equals y plus 173 divided by 94 times 94. We have a cancellation going that way, so the denominator is eliminated. On the left, the calculator already gave us the value, 1316, equals y plus 173. I wrote down the equation again down here just so we know what it originally started as. Any questions on that first step? Okay, now to isolate y, we have to take the opposite operation right here. Subtract 173. On the calculator, this is all we would do. Go minus 173, and our work is complete. It's pretty much just going to be those two steps. Each time we work the z-score equation, solving for y. On paper, it looks like we made a mountain out of it versus what we see in the calculator. It would look like this. Subtract 173 from both sides. This long bar is just saying tally both sides of the equation. Cancellation here tells us y equals. This number was 1143 in the calculator. So we want to replicate that with our new information. This is what the algebra looks like if you're writing down algebra on paper. But it's really just these two steps you see right here on the calculator as well. Does that make sense to folks on solving that equation? Okay, well, let's do this again on the actual problem B itself. Problem B says, suppose that the temperature high on September 13th has a z-score of negative 1.73. Just because it said z-score, here's a good strategy. Start by just writing down the z-score formula. It's down below for reference. I'm going to keep the left side and just the right-hand side. So I'll drop the part in words. Z equals y minus y bar divided by s. Or y minus the sample mean divided by the sample standard deviation. We want to know what was the temperature that day. But the temperature that day following the color coding is the unknown y. So if this was an exam question, because it's really kind of just a formula and algebra problem, if this is all you had on the exam, let's say it's a 5-point problem, that's worth partial credit because it tells me when the word z-score comes up, this is what's relevant to the problem. So that could be even 2 points of partial credit already, just dropping that in. Next step, putting in the information is worth partial credit as well. It said the z-score is negative 1.73, and that goes in for z on the left. Kind of weird this time, we're filling in the z-score. Negative 1.73 equals y minus the y bar, which is 11, hang on, I noticed a problem here. Let me fix my color coding. I need to get out of that habit. Y bar should be in blue. That nearly made me grab the wrong number. 76 degrees. I think I've made this comment before. Color coding is no good unless we're consistent all the way down. So sorry for that distraction there. 11.1 degrees goes in place of S. And this is worth partial credit too. If it was a 5-point problem, I'd say this is worth 3 points. We didn't get to the punchline, but you knew what the formula was, how to evaluate it. Last bit is just solving it. I'll do it 2 ways. First, let's replicate the calculator strategy. It's really just 2 things. You take the number on the left, negative 1.73, immediately multiply by whatever's in the denominator, so times 11.1. You get the new number out, negative 19.203. Then you take the opposite what's here, we would be adding 76. So plus 76, and that would be our answer to the problem. So just those 2 calculator operations. Doing it on paper would look like this. It might feel clunky to put in a whole big parenthesis capturing the fraction times 11.1. So if you recall cross products from algebra, you can make cross products relevant here. You take this, and it literally multiplies across the denominator into the numerator on the opposite side. Usually it's plural, but there's no denominator here. But even if there was, it'd be a denominator of 1, and multiplying 1 across doesn't do anything. So it's better just to think of this as a halfway cross product. We're literally shuffling 11.1 over here and multiplying. That's what the calculator did. Negative 19.203 is the next thing you'd write down. Equals y minus 76. Then just add 76 to both sides. We now have our value for y. It's 56, let's see, to 1 decimal place. This rounds up to 56.8 degrees Fahrenheit. That'd be pretty chilly for a high. 56.8 degrees. But notice it still would be considered not that unusual. I mean, we do have chilly days in September. Let's take a look at that. For the highs though, 60, oh, there's a 56. That got pretty close actually. Of course, that's close to October. So yeah, 56 is not unusual. It did show up in the calendar. And if it was closer to a -2 standard deviations, that might have been way more unusual looking. We did it, folks. That's solving for the actual data value in question when you have a known z-score. Any questions at the moment doing that problem there? Okay, just because again, it's a new algebra problem, and this is supposed to be a statistics class. Everyone has a different algebra background. Let's copy this in. Just as a reminder, this is a valid way to do the problem as well. Anything extra you show on paper is helpful for the sake of partial credit, but if you're doing it this way, at least this is a definite procedure. So think of this as step one. That's a weird thing to circle because you needed both numbers really. So I'll say this is your step one. And this is your step two. No matter if you change these numbers in any kind of way, it's still the same exact kind of format, just different numbers involved. Well, we think we beat the crap out of that problem. That one's done. Any questions before we try out the next one? Okay, just for the sake of satisfying our curiosity, what really happened on September 13th in 2024? Nothing unusual except that the temperature was actually kind of warm, 69 degrees, still cold relative to the average, but not by as many standard deviations as we said. We said nearly 2 below, and that gave us the 56.8 degrees. So these are the kind of problems that you're going to see on the MyStats Lab kind of homework. Some of them it's computing z-scores. Occasionally you're giving interpretations like these, and a couple of them involve solving equations like this one. So we'll be sure to practice this again on the next problem. So the next problem is maybe not the most exciting context in the world, but we're trying to emphasize the formula more than anything, I suppose you could say. So here's the z-score formula, just duplicate again for the sake of reference. Sample mean will be in blue, standard deviation in green, and the data value in yellow. And here's our context this time. We have a random sample of 6 light bulbs. Maybe these are, well, LED light bulbs perhaps. Maybe they're Christmas lights. We're not too sure on the context. They were selected from a production line and their lifetimes were measured in hours. So not the world's most exciting data, but this one's kind of remarkable for 968 hours. This one's maybe slightly unusual for 769 hours on the low end. And we have a bunch of follow-up questions involving all this data. But first, before we do anything involving z-scores, there's some z-score questions down below. Notice the first thing you've got to have is the sample mean y bar, sample standard deviation s. So that's our first job here. Find the sample mean and the sample standard deviation. Really just kind of a refresher on the calculator doing this data entry. So hit the stat key, hit enter. Looks like I already cleared out my variables, so I'll just type these in. Okay, I think I've got all the data in. Anyone need any additional time? Okay, next step, hit the stat key, go over to calc for calculate. This is the part where we hit enter a whole bunch of times. Oh, and just to mention on the exam, everyone seemed to do pretty well on this, so that's awesome. The X bar is what we call the Y bar. That's always a weird disconnect in the class. Some books use X bars, some books use Y bars. Our book happen to go with the Y bar route. So Y bar is 117 point to 2 decimal places. We'll keep the 0.15 that's shown. Oh, that could have been me. Let me double check my data. Thanks for mentioning that. That's kind of exciting in a way, because this is kind of struggle with doing this process, getting all the data in right. So let me check them one by one. 968, 893, 769, 845, 922, 915.
Not L3.
Oh, that's weird. Thanks for mentioning that. That was totally invisible to me as an issue there. I thought my calculator was in a normal form, but no, that's the wrong column whatsoever. Let's fix this. The first thing I would do to undo this weird issue is hit the stat key. If something weird ever goes on like that for you and your calculator, that's what this button here is. Kind of like just a reset. Hit enter on that a couple times. Now let me go back to, if I looked at that data carefully and used the smell test on this, an average of 117 hours doesn't make sense when all the data values are in the above 700 hours. So already I should have noticed there was a problem. I was just following along what the calculator told me. It's not the best way to do this. Looks like I still have L3. It's just clear over there. Let me just kill this off. Sure, when you go to enter in, you could change things to L3, but I think it's convenient to just make sure everything goes into L1, so it's always consistent the same time you run the calculator. So sorry for the delay. Let me get these in again. 968, 893, 769, 845, 922, 915. Okay, now we've got an L1. Again, good eye on spotting that there. That was a mistake that I don't think I was going to see, no matter how long I stared at it. Finally, that looks reasonable. My sample mean came out at 885.3 repeating. Does that look better to folks so far? Awesome. And looking at the data, yeah, that looks kind of crazy as a number to cite. The sample mean is supposed to be the center, and 885.33 hours looks like it would qualify a little bit better. We also have the sample standard deviation here. That's the SX. It comes out as S equals 69.68 hours. So now that we have that out of the way, we can start doing the problem. I think this might happen in the homework as well. Oftentimes, though, look through the reading and they'll indicate a sample mean, a sample standard deviation in the context of the problem. They might not always literally write down Y bar equals. So sometimes it's just saying the sample mean is, and you have to know that's your Y bar. So that's kind of like a vocabulary thing already on its own. So here's the next exciting part of the problem. Suppose another randomly selected light bulb is tested. This runs for 693 hours. How many standard deviations away from the mean is this observation? That's a confusing question, right? When we saw this kind of problem before, it just straight out asked us, calculate the z-score. And so we did. Notice how this problem is written. It says, how many standard deviations away? So what we have to know is, the z-score itself tells you that number of standard deviations. So some of the questions in the homework are really vague because the homework is trying to force us to connect the dots through the interpretation and the way they ask the same question. It's still the same problem. Z is the number of standard deviations. We just had to know by the wording, we're doing this, Z equals. Does that make sense to folks on the wording of this one? Let me point at it with the arrow just for emphasis. Well, once we're through the vague wording of the question, vague intentionally, unfortunately, on this one, just making us focus on the interpretation, we can go Y minus Y bar. divide by S. So now we're basically done with the formula above. We've used it up. We know what all of our information is, except one. Has anyone spotted the value for y in this problem? Yeah, good call. The data value, again, sometimes that's the confusing bit here. What is the data value? It's the thing where the question is relative to. We want to know how many standard deviations away from the mean is this observation, referring to 693 again. So that's the part of the question we're going after. So that's the data value. Y. Now we just plug everything in. So drop everything in as it's color coded, 693 minus, place a Y bar, 885.33, divide by S, 69.68. Really, this is only our second z-score we've calculated so far, so that's kind of exciting. Let's put this back into the calculator. Let's put it in one shot, so a slightly different way to compute. If I wanted this all in one line in the calculator, we have to start with parentheses because of the fraction being one entire group. So parenthesis 693 minus 885.33. Close those parentheses there, and that's the numerator. Hit division by 69.68. It's kind of annoying how part of your computation disappears off to the left. Actually, the T83 just would put a new line down below, which is convenient. So if you have to see your calculation, just use the left arrow to bring it back. Or if you need to see the right side, use the right arrow to bring it back. And we get this. That's really, really unusual. It's approaching 3 standard deviations below the mean. Below because we see the negative value, but also because 693 is just less than 885, so it's certainly below the mean. We weren't asked to interpret it in any way, but that's good to note here on the notes. That's pretty unusual. So it is, to 1 decimal place, negative 2.8, rounding up. Standard deviations below the mean. Deserves an exclamation mark because, again, that's pretty unusual for these data. And so by our rule of thumb, this is very unusual. If we use the 1.5 IQR rule of thumb, that's almost certainly going to be flagged as an outlier by that rule of thumb as well. Well, we're nearly done with the problem. Guess it didn't have too many parts. Any questions with our computation so far? Okay, so this one is a really confusing question. The z-score for another randomly selected light bulb is 2.18. You know, I don't really even like the way this question is written. Usually I like to write questions where you're giving one answer per part. This one has 2 answers that you have to just know to put down. That's easy to miss in an exam, for example. The first question we have to answer, I think this is similar to problems in my lab statistics. If the z-score for another light bulb is 2.18, how many standard deviations away from the mean is this light bulb? Anyone see the resolution to that question? Exactly. It's one of those weird questions where it feels like we should be doing something, but it's just a reminder the z-score is that number of standard deviations exactly. So for this part right here, this light bulb is 2.18 standard deviations. And you could just repeat away from the mean. That would be full credit for this kind of answer. This would maybe be part D to make it a separate problem. But let's say above the mean. Just as a reminder, if the z-score is positive, that means it's larger than 885.33 in its runtime. It's also pretty unusual at 2.18 but I wouldn't say very unusual, maybe somewhat unusual for an observation. Because it's more than 2 standard deviations away by a pretty significant chunk. So that was one part. The other part is finding the actual lifetime of this light bulb. So to do that, we have to solve one of those equations again. Just to organize the responses, I'll write down here, the lifetime is y equals, and we'll come back to it. We need to fill that in just a moment. So to solve this, we rewrite the z-score formula. Z equals y minus y bar divided by s. First tricky thing about this one is we have to know in place of z, we're throwing in that quantity. So that goes there. And then this becomes, let me go to the right since I'm running out of vertical space, 2.18 equals, wrong highlighter there, let me try again. We'll put y into this position, minus y bar is right there, but you know, with the weird game of telephone, I could have copied it wrong. It's good to see the original data. 885.33 divide by. Next thing to jump through is wherever s was, find it on paper, put it in the denominator. 69.68. My fraction bar looks a little crazy. Let me fix that there. So this is how it would come together. Let's take those calculator steps to show rapidly what this would look like for a solution. So step one in this process is to perform the so-called cross product. The denominator is going to multiply a cross equality into the left-hand side. But let me look at that left-hand side. Yeah, 2.18. So take 2.18 times 69.68. We get a big number. We're rounding this to 1 decimal place. So standard advice is go 1 additional decimal place. Or if you're the careful person, just take the entire digit they gave you. This would be sufficient though. Go 151. Let me get the right pen. 151.90. We'll round our final answer to the 1 decimal place. Equals y minus 885.33. So that's halfway done. Oop, I'm not sure what I did there. Last thing to do is just add 885 to both sides of this equation. But the calculator is ready to go for that step. You literally just hit plus right away, 885.33. And this is the number we'll take. This one will round to the 1 decimal place. So this will come out as 1037.2. These were light bulbs with hours in runtime, so this was in hours, equals y. So finally we did it. If another randomly selected light bulb in this production run had a z-score of 2.18, that's really unusual. It's 2.18 standard deviations above the mean. That's this part of the question. Again, it seems kind of silly, but it's confusing unless we know we're just connecting literally. Z-score is the number of standard deviations. But the actual lifetime of this light bulb was that value, 137.2. It feels weird to leave it hanging here, so I'll recopy it on this spot as well. 1037.2 hours. Looking at the original data, nothing even broke 1,000. So it's in that way that 2.18 standard deviations is pretty unusual. And it's in this way that negative 2.8 standard deviations was tremendously unusual as well. Well, any last questions, folks, on doing any one of those computations? Okay, so these are z-scores in a nutshell. So far, our feel about this is the most practical use of with z-scores is it's just another way, kind of like the 1.5 IQ rule of thumb, to tell when things are far away, potentially outliers, unusual observations that stand out. But there's actually bigger reasons for the z-scores that we're going to see. And z-scores actually show up in formulas later on in the course when we're at the end part doing inferential statistics. But for a really fast application, here's a decent one. Maybe not the most pivotal and exciting application, but you can imagine that this is a realistic kind of problem. Reading through the context, it says a student took 2 national aptitude tests, maybe something like the ACT and SAT tests for examples. Seems like that could have been what these numbers are representing. They then tell us the mean and standard deviation were 475, 100 respectively for the first test and 38 respectively for the second test. If you're like me, you're probably already lost. That's like a cloud of numbers, and they use words respectively a bunch of times. Students scored 625 on the first test, 45 on the second test, so even more information. Use z-scores to determine on which exam the student performed better relative to other test takers. So what's the better score, 625 or 45, is the question. I think our book puts this in a really nice way. Z-scores let you compare apples to oranges in a very, very literal way. And this is kind of what we're doing on this problem. But when you're given just a cloud of information like this, the organization is the fundamental strategy now. This will be helpful when you see these problems as well on MyLab statistics. It's overwhelming seeing basically 6 numbers just flying at you. So what I would do is just break this up into a 2-column system. There was 2 tests, so let's separate this out as test 1, test 2. We're going to start splitting up this information. Mean and standard deviation comes up, but the way they give the mean and standard deviation is kind of inconvenient. This word respectively, it's a nice word. It's kind of magical. It can make it so that you write half as many sentences as you would have otherwise. It's compacting the information down, but it also has the potential to be confusing. So when we said the mean and standard deviation were 475 and 100 respectively, this word respectively causes a kind of correspondence. The numbers that come first are referring to the means. So it's a one-to-one correspondence in that way. That's what the word respectively is trying to indicate. And the numbers that come second, standard deviation, are associated as well. So if we list this out, mean, standard deviation, and then give 2 numbers and say respectively, we mean those 2 numbers were again the mean and standard deviation in that specific order. It's kind of annoying, right? Sometimes it's helpful because you're not writing as much when you use the words respectively. But if we're the ones unpacking the data, it's easy to get this mixed up. So this is all for the first test. Let's carefully write down. Mean is y bar is 475. Standard deviation is S, which is 100. Then it says 30 and 8 respectively for the second test. So there's that word again. When it says respectively, same correspondence. The number that came first here is the first descriptor that came first, the mean. Number that came second, 8, is the second descriptor that came second, standard deviation. So you could call this is now for the second test, y bar equals 30. S equals 8. I think if I was to write this out as a real exam question, I wouldn't be that annoying. I'd probably would say, for the first test, the mean was 475 and the standard deviation was 100. For the second test, the mean was a 30 and the standard deviation was 8. I think I would write out that way. But on the homework problems, we have the extra time and mental space. We don't have the stress of exam to unpack this kind of stuff. And this is how people do right. So it's good to unpack this just as a skill on its own. Does that make sense to folks on how we got these values separated out? Okay, so pull out the data methodically, carefully, organize with 2 columns, and it won't be too bad. Here's the second part. This is giving us the data values, y. The student scored 625 on the first test, so they're not using the word respectively anymore. That's, thank goodness. So 625 points on this test, 45 points on the second test. So y equals 45 on this one. So already, if you're looking at this, depending on your number sense, you might already have a feel on which test the student did better on. 625 points looks impressive relative to a mean of 475. 45 points maybe doesn't look too impressive relative to a mean of 30. But if all you're comparing is the data value against the mean, it's never the full story, like we mentioned. Standard deviation is equally important as the mean itself. That's one big kind of theme that goes along with these two statistics. So we won't know for sure unless we calculate the z-score. This might look better than this one, but the numbers could be deceiving. I kind of forgot. So let's calculate which one is actually better. Either case, we're using z-scores, so let's write them in. So here's the formula on the left. Duplicate on the right. Kind of feels tedious writing down this formula like 7 times now at this point, but you know, your subconscious has a way of hanging on to things you write down. And if you've had this formula memorized, it's just on your page of notes just as a backup, just to make sure you didn't get anything mixed up. So the value that's y is the 625 on both of these. So on the first z-score, it's 625. Minus, see the table information above, 475 for the mean. Divide by 100 in the standard deviation. Usually when I go to do these computations, I personally would just do it this way. 625 minus 475. Hit enter. Just don't forget you hit enter. So you do the subtraction in the numerator. Divide by 100. And we get 1.5. Standard deviations above because the number's positive, the mean. So that's our z-score on that one. Let's do it again over here for this z-score. First, any questions on finishing out the column on the left? Okay, algebraically, same exact process, different substitutions. So methodically cite the data above. Notice if you didn't write this out once and you were pulling it out from a problem, I personally mix this up very, very easily. It's just too much information. And I would probably be reading the problem a whole bunch of times just to find out, okay, which one was test 1, which one was test 2. Doing this just gives your eyes a break. It zeroes in what information you're really using. It'll make you way, way more accurate when you go to apply the formula below. So go 45 minus y bar, which is 30, divide by s, which in this test 2 was just an 8. We'll have in the calculator 45 minus 30. Hit enter to compute, then divide by 8. And this is 1.875. Standard deviations above the mean. That's not quite unusual, but it's starting to get borderline becoming unusual. That was a really high score. This one was more kind of the middle of the road. So once we see z-scores, which one would you say did the student do the best on? Was it test 1 or test 2? Yeah, definitely test 2. Good call, folks. Test 2, it's the one with the higher standard deviation. It's the one that is the most unusual. It was that score. So we just have to finish it off to say the student performed better on test 2. Then that finishes out the problem on this one. Lots of ways to do this kind of problem. You can imagine a different scenario where maybe you're a veterinary doctor and you have a Dalmatian come in, you have maybe a boxer come in. They're both underweight, and maybe these are two medical emergencies that happened at the same exact time in your office. Stuff like that happens. If you know the mean and standard deviation for the breed and weigh both of these animals, you can tell which one is the most underweight, which one is the one that deserves your attention the most. So even though this problem doesn't seem to have high stakes, it can be used in pretty high stakes situations indeed. But this is where the notes end. These are the kinds of things we'll be doing in section 5.1. Any questions at all before we close out these notes? Okay, before we get into the meat of chapter 5, the normal model using the z-score, we have one extra section, 5.2. I think it's the most confusing section in this entire chapter, but it's still important. We're going to take our time with it. The information here is kind of surprising and shocking in a way. When I ran these problems through, oftentimes students really don't quite feel like it makes any sense whatsoever. The ideas with shifting and scaling. In fact, over the years, I put in this set of 3 pieces of data as a demonstration of what's really going to happen to the data when you shift and scale it. So we're going to verify with our own eyes, seeing is believing, on how these properties really work. We'll put them into play by applying formulas to our statistics and see how the formulas work. So first, let's see this in words. Again, this is surprising information. And the most surprising information is shifting the data. So if we shift the data, what we mean by that is we take a data set and add or subtract the same exact number to every single observation. I think for the light bulb data, we added 100 hours to every single observation. We've shifted all of the data to the right. If we shift all the data to the right, then the measures of position will shift by that same constant. So adding a constant to every data value adds or subtracts that data value, that constant to every measure position, but leaves measures of spread unchanged. We can add the same constant to all of our data, and these things will never change. And that's the thing that's most surprising on these notes. It's almost debatable that this really happens unless we compute it and see it ourselves. But the notes is already vague and confusing. It's kind of a summary section as well. What are measures of position and what are measures of spread is what example 1 is all about. Because if we don't know what those are, we can't really apply these ideas. So let's reread this after we know exactly what we mean by measures of position versus measures of spread. Actually, the measures of spread are a little bit easier to identify because there's not very many of them. The first measure of spread, how spread out our data was the most blunt measurement of all, and we've only used it once in this course. It was called the range. It tells you how spread out the data is because it calculates the distance from the maximum to the minimum. By formula, it was max minus min. And thinking through this, if I add a constant, say 10, to all the data, I've also added 10 to the max, I've also added 10 to the min, the range wouldn't change. That's what it means when it says measures of spread is unchanged. That's one measure of spread. The other one we saw in this course, anyone happen to recall what it was? Good call, absolutely. Less blunt than this is a good measurement, IQR for interquartile range. It takes the position, quartile 3, 75th percentile, minus the other position, quartile 1, the 25th percentile. And it's just, well, literally a range, it's in the name, the distance between those two quartiles. Anyone recall the final measure of spread? kind of a tough question because it's a lot of statistics just sort of floating out there. Good call, absolutely. We're just collecting them all in one spot in the notes. S, that's our last one. That's the one we were using relative to talking about z-scores. So S equals the standard deviation. So those are all of our measures of spread. If we shift the data, measures of position will change, but measures of spread are left unchanged. So in other words, if these are our data, and we shift the data by subtracting 5 from all the data values, the mean would change. It'd be reduced by 5. But the standard deviation does not change at all. Again, it's kind of shocking, especially when we put it into practice in a formula. It's going to seem like we're just violating math and doing things incorrectly, but we're just following this same principle right here. So those are measures of spread. Next thing we're going to collect are all of the measures of position that we've seen so far in this class. The ones that we mentioned the most are the center. So 2 ways to measure the center would have been the sample's mean, y bar, or the sample's median, m. But you know, maximum is a position, and so is minimum. So are quartiles 3 and quartiles 1. So if the median measures the center and it's a measure position, quartile 3 is just measuring the 75th percentile instead of the 50th percentile. So there's a lot of measures of position. They go, if we were to list them all out, versus the 5-number summary, the whole list is in there. The minimum is a position. Quartile 1, let's rewrite this as the 25th percentile just to connect that concept. The medium M, which is the 50th percentile. Quartile 3, which is the 75th percentile. Maximum is the other measurement of position. It's the highest position of the data set, in other words. And then last but not least is y bar, the sample mean. Or if you say sample average, it's always good to remind ourselves, same exact concept. So this is like a cheat sheet for us at the moment. We'll often refer to this. This is something you might want to refer back to when you go to do the problems in section 5.2 as well, because we're going to apply both of these ideas at once. And so when you are given a random statistic, you have to think in your mind right away, was that a measurement of position or was it a measurement of spread? Getting mixed up here will get us mixed up on this theorem above. And by the way, a theorem is just a way to say fancy mathematical fact. We'll have a couple interesting theorems in this course. So now all the position measurements, all the spread measurements are on the table for us. The reminder is we add or subtract the same constant to every single data value in our data set. We add and subtract the same constant to all of these statistics here. However, nothing about the spread changes, not the range, the interquartile range, nor the standard deviation. That's kind of remarkable in a way. If we rescale the data, we haven't talked about this one as much because shifting is the confusing one, but rescaling the data is kind of the normal thing. Nothing unusual happens here. Rescaling means you're either multiplying or dividing all the data values by the same constant number. Say you're multiplying all the data values by 2. Then all the measurements of position are multiplied by that same constant, and so are all the measurements of spread. So if I took just some random data set and multiplied every observation by 2, every single statistic on the table here is multiplied by 2. Thank goodness, that means nothing funny is going on. This is the one to worry about. Shifting the data is weird, and it's weird because of this part right here. This is the most confusing part of the notes, because when this comes up, it's just strange how we're using a formula. It's a way you would never use a formula in a normal math class, a normal chemistry class, biology class, and so on. But if those classes were talking about measures of spread, they absolutely would have to use the formulas in the way we're about to. Well, I say about to, but I've got about 5 minutes, so we'll see how much time we really have on this. Any questions at the moment, folks, with this dichotomy here, position versus spread? Okay, well, because we have limited time, I want to just give you a preview of what makes this truly very confusing. We'll come back to this and fill it out in full. We'll go through the demonstration because this really connects those thoughts in our mind when we see this, seeing is believing, like we mentioned. But let me give you a preview of some of the confusion here. Here's a study of 130 healthy men and women, and in that study, they found that the mean temperature was 98.25 degrees Fahrenheit when they measured body temperatures. Standard deviation was 0.73 degrees Fahrenheit, so not a lot of spread. There's also information on the minimum temperature. Maximum temperature is concerning. Someone might have had a fever, infected people, who knows? Maybe that's their normal body temperature. They're just an unusual person. And let's suppose that you're publishing this in a journal that only uses Celsius. Here's the conversion formula to go from Fahrenheit into Celsius. The format of the formula is not convenient. We'd want to rewrite it as C equals, distribute 5/9 inside the group. So 5/9 times F minus 5/9 times 32. Oh, geez, that's algebra nowhere. That's negative 160, arithmetic rather, over 9. So if we expand the formula, this is what it looks like. This part is rescaling because it's going to multiply all of the 130 Fahrenheit observations by 5/9. Rescaling is either multiplying or dividing. This part is shifting. It's shifting because it's subtracting 160/9 from all of the 130 Fahrenheit temperatures just to get it back into Celsius. So the instruction says, find mean, standard deviation, min and max of the temperatures in Celsius. I'll put this in orange, so we'll recopy this when we are back with a fresher mind. Well, let's focus on standard deviation. That was a measurement of spread, right? So S in Celsius, I'll just write C for Celsius, is C equals 5/9 times, we go to the temperature, 0.73 was that standard deviation, 0.73, and that's the entire formula. We totally ditch this part. That's really weird, right? We have a correct formula, but that formula involved a shifting of the data. And shifting does not change your measurement of spread whatsoever. Standard deviation is a measurement of spread, so that's the right formula. This is bizarre in a way because it goes against your mathematical training of using the whole correct formula, but that's context sensitive on what you're actually evaluating it against. Does that make sense so far, or does it seem just kind of weird in a way? If it feels weird to you, that's how it felt for me when I first saw this. It just seemed totally unlogical to ever do that to a formula. For all the other statistics, min, max, and mean, those are measurements of position. It didn't matter if we rescaled or shifted, you use the whole entire formula. These are the weird ones, where anytime you're doing rescaling, shifting, it leaves that part totally unchanged. So we'll come back to that, work out a couple examples with those same kind of information, practicing how all this goes. But any questions or comments at the moment?
So what, in that one right there, what were you were shifting, you just,
At the very top or right
right,
here?
no, right here in this problem.
Yeah.
You were shifting the,
Yeah, this is the shifting, subtracting by 160/9, because this part of the formula would subtract the same constant from all the observations, the 130. So that's the subtracting, the same constant from all the observations. But if you do that, it'll leave the measures of spread unchanged. That's why we don't have the minus 160/9 here. it's bonkers in a way. It's really going on faith practically, right? It just says that's how it works. But we'll see it in the actual data. We'll calculate this ourselves and see how that really works.
I guess this is kind of hard to see where you got your,
Would it be the 5/9 or the
yeah, that's
0.73?
just for, that would be just pertaining to this, right?
Yeah, that was just the rescaling part. So it said rescaling the data is going to multiply all the data values. It'll multiply the same constants to all measures of spread. So since the standard deviation S was a measure of spread, that part was the rescaling. So we rescaled 5/9 again here again on the 0.73.
Oh, so where it says F minus 32, that's your 0.73? No?
Oh, the 0.73 came from right here.
Okay,
And yeah, that was another thing we did on this formula. There was just too much going on with it. This is hiding what part is the shifting and which part is the scaling. So we just rewrote it in this way. We multiplied 5/9 inside, and the 5/9 times the negative 32 gave us that part, the negative
Oh.
169.
I'm with you now, I'm up to speed on here.
Gotcha. Yeah, it's a kind of a nasty problem in a way. Other questions at the moment?
Thank you.
Yeah, absolutely. Thanks for mentioning that. We'll come back with this with a much fresher minded perspective on Monday. Look through the demonstrations and then try it again on a different problem, just another redo of that. But have a great weekend, folks. If you have any questions working on the quiz 4, I'll be happy to help out. Otherwise, we'll be right back here on Monday. Have a great time. I'm going to erase some of this since we'll start off fresh when we come back as well.
Okay, here's my quiz.
Awesome. Thank you.
You're welcome.
Have a great weekend. Hey, how's it going?
Really good. Just had a quick question. There's a home due today. I can't remember what part. I think
Let's see
it
here.
was after the chapter one.
So yeah, that sounds like the chapter 3 stuff. So the 2A contingency tables.
I think so, yeah. It's the lesson after we got done with 3.5, I think.
Yeah, so yeah, that would be that one for sure.
Yeah, I think it's due today. Will I still be able to receive full credit if I get it done tomorrow?
Yeah, absolutely.
Okay.
Yeah, my due dates are really just pacing sake. I know honestly, when you're getting through an exam, I think it's kind of normal to do a little bit of catch up afterwards. I mean, that would tell me you focused on the exam, which is the right strategy for this class. And so doing a little bit of catch up on the prior sections, no big deal. That's one of the reasons I don't put grade penalties in for that stuff. So yeah, you'll still get full credit, absolutely.
Because I want to catch them sleep.
Yeah, I hear you. Yeah, I mean, it makes learning more meaningful too. It's hard to really retain anything you're doing at like 11 a.m. or anything, or 11 p.m. rather.
Yeah, I mean, I can get it done and as much time as I need to get it right, but the next morning I'm not gonna remember the thing.
Yeah, exactly. So yeah, no worries on that. Thanks, you too.